Hello and welcome back. Today we'll be watching this video. It's an OMC video, props, where power meets the water. Richard D. Sent me a message on the YouTubes asking about propellers. Rather than trying to answer it, I just decided I would post this. Reason I stopped posting it is some dude on Facebook has been downloading them and then posting them as his own. And then he gets all kinds of praise, like, oh my God, thanks, where'd you get this stuff? And he's like, well, I've been collecting OMC stuff for a while. I just have it in my collection. Yeah. Now, here's the problem. He's not the one wasting his money on this useless junk. I am. That kind of bothered me. But so anyway, I stopped uploading them. But then I got over it, and here you go. Have a fun watch.
Your customers demand performance. You probably don't need me to tell you that. In fact, if you're like most dealers, you think about performance whenever you're rigging a boat for your customer. You know how the boat's design and engine characteristics will affect the rig's performance and handling. You may know which accessories will give your customers more bang for the buck. But do you really understand the role that the propeller plays? The prop plays a crucial role in the boat's handling and performance. It is, after all, where the power meets the water. The wrong prop can cause unacceptable performance, poor handling, poor fuel economy, and can even damage the engine. Because of this, when you're rigging a boat, you must choose the right style and right size prop to make sure the boat and engine will deliver everything they're capable of. But that's not always what happens. Occasionally, a boat and engine rig will be delivered to the customer with whatever prop the prop chart recommends. This can be a big mistake. The prop chart is intended only as a starting point for a test on the water. If you accept as a gospel, the boat may not run up to snuff and you'll have a damaged engine or an unhappy customer on your hands. The wrong prop can waste fuel, waste performance, and even waste the engine. I'm Mike Ropanek from the OMC Service Department. In this videotape, we will look at the design characteristics of propellers. We'll discuss how they affect performance, both in outboard and stern drive application. We'll also demonstrate how to prop out a boat in an on-the-water test. When you install a prop, you can't be sure of how the engine and boat will react. There's just too many variables. The boat size, the weight, load distribution, hull design, the intended use, the engine's power characteristics, or how much gear case is in the water, and so on. You can use charts and other calculations to choose a prop, but the only way to be sure is to test it on the water. If you understand certain design characteristics of propellers, it'll help you to choose the prop that will deliver the optimum performance for the boat's intended service. First of all, let's look at how a propeller works. Simply stated, a propeller is a screw. When we submerge it in the water and rotate it, the blades push the water away. This water pushes against the surrounding water to move the boat forward. If we look at some of the parts of the propeller, we can understand how they affect the prop's performance. The blade is the part that actually moves the water. The blade is the thickest at the hub and gets thinner as it gets to the blade tip. The blade area has two main functions. The blade back, which is the side closest to the boat, creates a low pressure area as the prop rotates. This low pressure helps pull the prop forward. The blade face, which is the side opposite the boat, creates a high pressure area as it rotates. This high pressure forces a stream of water called a thrust cone to the rear. This thrust cone pushes against the undisturbed water around the prop and moves the boat forward. The leading edge of the blade is the area that first makes contact and cuts through the water. The trailing edge is where the water leaves the prop to form the thrust cone. At the center of the prop is called the hub. If you look at the hub on an OMC prop, you'll find a number. This one says 14.5 by 20. The first number, 14.5, is the diameter of the prop, measured at the tips of the blade. The second number, 20, is the pitch or the angle of the prop blades. Imagine for a minute that the water is a solid, like Jell-O. If you turn this prop, one full turn, it will move approximately 20 inches through our Jell-O. Of course, the water is not a solid, and the prop will slip a little, but not as much as you may think. We won't get the full 20 inches, but in most cases, we will get about 16 or 18. If you look at the OMC prop chart, you find that diameter usually increases as the pitch decreases. This gives us a good selection of props, so we can pick one that will provide the best match between the engine and the boat. Let's take a moment to clear up some poorly understood terms, ventilation and cavitation. Ventilation occurs when external gases, such as surface air or the engine's exhaust, get into the propeller blade area. If a prop is pushing air, then it isn't pushing as much water as it should, and this causes a loss of thrust, an increase in engine RPM, and poor boat performance. Ventilation can be caused by running the prop too close to the surface, the wrong trim angle, severe port or starboard turns, large keels, foul boat bottoms or lower units, hull protrusions such as transducers, or loss of the converging ring from aluminum propellers. Cavitation happens when rough or damaged areas on the prop disturb the smooth flow of water. As water flows around the damaged area, it is deflected away, increasing the speed of the water and creating a low pressure area. This low pressure causes the water to boil and turn to vapor. These vapor bubbles move into the high pressure area behind the blades. There they collapse back into the water, creating tiny high-speed impacts on the blade face. The end result is a pitted or eroded area on the propeller. Cavitation can also happen if the prop is loaded too heavily due to a poor design or incorrect application. It can be prevented by making sure that the prop is correct for the application and that it's in good shape. No dings, dents, or other defects on the leading edge of the prop blades. Ventilation, on the other hand, can be a little trickier. To deal with this on some props, the trailing edge is curled. This is called blade cup or cupping. The cupping forms a seal to help prevent bubbles on the low pressure side of the blade from reaching the high pressure side. By reducing ventilation, this lets us trim out further. If it's an outboard, cupping allows us to raise the engine on a boat's transom to improve performance. The cupping may have the effect of adding as much as 2 inches of pitch to the prop. This can reduce engine speed by as much as approximately 150 to 300 RPM at full throttle. Most OMC outboards and stern drives feature through hub exhaust. Exhaust gases travel between the inner and outer hubs of the prop. This reduces exhaust noise and back pressure, which means a quieter, more powerful, and more efficient engine. On some OMC props, you'll see some kind of a ring at the rear of the hub. Most aluminum props have a converging ring, and some stainless steel props have a diverging ring. These rings reduce exhaust back pressure, and as well as preventing engine exhaust gases from getting into the propeller blade area. As the gear case moves through the water velocity around the gear case increases. This creates a low pressure area around the gear case and the prop hub. Since the diameter of the hub is smaller than the gear case, it lowers the pressure even more. The engine's exhaust tries to migrate to the low pressure area where it can reach the blade area. The converging ring or diverging rings help form a seal between the exhaust and the blade's working area. Neither ring will hurt the prop's performance. However, if the ring is left off, the exhaust may cause ventilation, and you may gain about 200 RPM and lose 2 or 3 miles an hour. Another design characteristic of propellers is rake. Rake is the angle of the prop blade relative to the hub. If we cut the blade on a line extending through the center line of the prop, we can see the rake angle. The raker's blades are swept back at a curved angle that averages 20 degrees. This sailboat prop's blades are swept forward. Here the rake angle is -5 degrees. Most OMC propellers fall between these two examples. Some props have a large amount of rake to lift the bow of the boat. When you trim the engine out, the engine's thrust is directed downward, forcing the bow of the boat up. But there's another force at work here. The water is now entering the prop's working area at an angle rather than straight on. The blade's rake changes the effective pitch of each blade as the prop rotates. For example, when you trim out a 24-inch raker prop, the effective pitch may be 22 inches on the top blade and 26 inches on the bottom blade. This exerts an additional downward force on the prop, which helps to lift the bow of the boat. While some OMC props have considerable amount of rake, others have very little. Some racing hull designs depend on air to lift the bow and use the prop's thrust to raise the stern. Outboards can be mounted high on the transom, so the top of the prop blade is breaking the surface of the water. The prop's rotation has a paddle wheel effect that creates two forces. First, it tries to force the engine to starboard. The driver compensates for this by steering to port. Second, when the blades hit the water on the starboard side, they force the stern of the boat up. Coming out of the water on the port side, the blades create a lot of spray, but they really can't push against the air, so there's no downward force on the port side to counteract the lifting force on the starboard side. These props are called transom lifters. Stern drives cannot be raised on the transom easily, but in some applications a transom or bow lifting prop will still improve performance. Many high-performance props are designed to ventilate at low speeds. This allows the engine to build up RPM and horsepower, getting the boat on plane and up to speed faster. Some of these props have holes drilled through the outer exhaust tub to allow exhaust gases to ventilate the blade area. At higher speeds, water rushing past the hub seals off the vent holes, preventing them from ventilating the blades. Other racing props use an over-the-hub type exhaust design. All the exhaust gases escape around the prop hub, ventilating the prop on takeoff. These props are intended for very light boats and high-speed applications. The number of blades on a prop represents a trade-off between efficiency and smoothness. Theoretically, the fewer blades a prop has, the more efficient it will be. But props with more blades will run smoother. You'll notice that most OMC props have 3 blades. For most applications, this is the best balance between efficiency and smoothness. Some high-performance props have 4 blades for increased blade surface area. The material used to make a prop affects its design and application. Aluminum propellers are lower in price than the stainless steel and have a reasonable durability. If strength is what you need, the stainless steel prop is your choice because it's 5 times stronger than the aluminum. Stainless steel props may enjoy a performance advantage too. The extra strength allows us to make the blades much thinner so they move through the water more easily. Finally, never forget that no matter how carefully a prop is designed, it won't do the job if it's damaged. Props that are damaged by hitting rocks or other underwater objects should be repaired or replaced immediately, even if it's just some minor nicks on the leading edge. It can have a dramatic impact on the rig's performance, even cause an engine damage. Props which are severely damaged, as this one is, should not be run at all. They can tear up a gear case in a hurry. Encourage your customers to carry a spare prop. If they hit something, it just might save the day. When selecting a propeller, you should first study the OMC propeller chart in the OMC parts and accessory catalog. By referencing engine horsepower and year, the boat's length, hull design, and intended use, you can find a good starting point for your on-the-water tests. Don't forget, what the prop chart recommends may not always be the best prop for the boat. You must try out the prop on the water, use an accurate tachometer, such as the OMC quartz tach, and an accurate speedometer. If you have a programmable tachometer, be sure you use the correct setting for the engine's charging system. On power trim and tilt models, a trim gauge would also be helpful. Your goal is to come up with the best combination of boat performance and correct engine RPM range. We've been talking in terms of outboards throughout this program, but it's important to remember that these principles hold true for stern drives as well. The propping out procedure for stern drives is identical to that of outboards, except that you cannot alter the outdrive's height on the transom without extensive reworking of the transom, a time-consuming and costly job. Before propping out the boat, you should check the condition of both the boat and the engine. The bottom of the hull, particularly toward the back of the boat, should be free of any hook or bowing upward condition, and rocker, which is the bowing downward condition. Any marine growth on the hull or engine should be completely removed, as it will reduce the boat's speed dramatically. You should also satisfy yourself that the engine is operating properly and producing its full rated horsepower. If you're propping out a used engine, you may want to check the condition first with a tachometer and a test prop. You must select a prop that allows the engine to run near the midpoint of the operating range when the engine is at full throttle. Prop the boat for its normal running condition with an average load and weight distribution. If the boat will be used for two applications, for example, water skiing and high-performance boating, it may be necessary to select two propellers, one for each application. If you're propping out an engine that has not been broken in completely, run the engine at wide open throttle only for brief periods of time. Be aware that under no circumstances should any engine, new or old, be allowed to exceed the upper limit of its RPM range. On outboards, the height of the anti-ventilation plate will also affect the boat's performance. For most pleasure boats, you want the plate to be as high as possible without sacrificing acceleration or turning performance. If you go too high, surface air will cause the prop to ventilate. For starters, mount the outboard so the anti-ventilation plate is a little below the bottom of a flat bottom hole, a little above the bottom for deep V holes, and even with the bottom for other holes. High-performance boats that exceed 50 miles an hour may not follow this rule of thumb. The engine height will be dictated by the speed range of that application. On a bass boat, for example, the ventilation plate may be 3 or more inches above the bottom when the engine is full down on the transom. Keep in mind, when raising an engine this high, you run the risk of lifting the engine's cooling water intakes out of the water. If this happens, you could overheat the engine and cause serious power head damage. When making these measurements, the anti-ventilation plate should be parallel to the boat bottom. These are good starting points. We'll show you why and how to change this. The anti-ventilation plate height on stern drive models has been determined by the boat manufacturer. Although it cannot be changed easily, it can be checked by referring to the specifications in the engine and transom bracket installation instructions. Finally, remember that you must never install an engine that exceeds the boat's rated horsepower. You can find the rated horsepower on the Coast Guard capacity plate. Overpowering a boat can result in loss of boat control, endangering the operator, passengers, or bystanders. If an accident occurs involving an overpowered boat, it will create a tremendous liability problem for you, the dealer. Well, we've talked about boats, engines, and props long enough. Let's go boating. For our propping out demonstration, we'll use a 4 winds runabout with an Evinrude V6. First, let's check the service manual to find the correct full throttle operating range. For this engine, it's 5,000 to 6,000 RPM. We'll make several runs in both directions on a safe body of water. We'll run at wide open throttle for brief periods to determine the maximum RPM and speed. We want to choose the prop that allows the engine to run near the midpoint of the full throttle operating range with a normal load. Remember that increasing pitch will lower RPM, reduce acceleration, reduce motor noise, and sometimes will improve fuel economy and increase boat speed. Decreasing pitch will increase RPM, improve acceleration, increase motor noise, and may reduce fuel economy and decrease boat speed. For our particular boat and motor combination, the parts and accessory catalog recommends a 15 by 17 inch prop. We found this gave us a top speed of 46.5 miles an hour at 57 to 5800 RPM. This is near the top of the engine's RPM range, so we'll try a 19 pitch prop. This should bring the RPM near the middle of the operating range and give us a little more boat speed. A 19-inch pitch prop gave us 49.5 miles an hour at 53 to 5400 RPM. So we gained a little boat speed and brought the RPM closer to the middle of the operating range. Just what we hoped would happen. Let's see what happens with a 21-inch pitch prop. We lost boat speed and RPMs with the 21-inch pitch prop, 48 miles per hour at 51 to 5200 RPM. Based on these tests, the 19-inch pitch prop is the best choice for this boat, motor, and loading combination. When you make your speed runs, be sure to adjust the trim to achieve the maximum speed. Trimming out the engine properly can make a difference of 10 miles an hour or more. This is an easy way to make some impressive gains in boat speed, especially when you're considering how much extra horsepower it would take to gain that extra 10 miles an hour. If you're propping out an outboard, you may also want to experiment with raising the engine on the transom. This may increase the boat speed by reducing the amount of gear case that you're dragging through the water. Of course, if you go too high on the transom, you may ventilate the prop and lose boat speed. And as I said earlier, you do run the risk of cutting off the engine's water supply. If you have propped out the boat properly, it will deliver optimum performance for the speed and load you have chosen. Always remember, however, that as conditions change, so might the correct propeller for the boat. If the boat was propped on a cool day with low humidity, that prop may not be right on a hot, humid day when the engine's power is diminished. Equipment may be added, making the total package heavier. As a family grows, their boating habits may change. This can change the boat's typical load and how it is used. Because of these changes, you may have to prop out the boat again to determine the best prop for the new situation. And keep in mind, there's a lot more to prop selection than diameter and pitch. For example, you wouldn't want to put an over-the-hub type exhaust propeller on a family pontoon boat. You have to look at the application to determine which prop will do the best job for that situation. The propeller is far more than just another accessory. It's a crucial part of the rig, and it can make or break performance and customer satisfaction. Select the best propeller design, choose the size that will maximize the boat and engine's performance, and you will be doing your best to satisfy the customer. Now that we've discussed propellers, let's take a look at 4 OMC prop designs. The OMC aluminum propeller, the SST2 propeller, the OMC Rake propeller, and last but not least, the OMC shooter propeller. The OMC aluminum prop is an economical choice for most boating applications. Most are cupped and equipped with converging rings, and they have a painted finish. The SST2 propeller offers the durability and performance of a stainless steel prop for most applications. They have a diverging ring to reduce ventilation, black finish, and double cupping, meaning there's twice as much cup. They're excellent for water skiing and general recreational and family use. The OMC Raker propeller is a high-performance bow lifting propeller with cupped high rake blades. It has ventilation holes in the hub for controlled ventilation to build up RPM and improve acceleration on takeoff. The extended hub prevents ventilation at high speed. This prop is designed to run at higher transom heights for best top-end performance with a through hub design. It's good for bass boats that require a lot of trim for best top-end performance. The OMC Shooter is a unique four-blade design intended for hard-to-plane, high-performance boats. It offers faster takeoff and mid-range acceleration and improved steering. Like the Raker, it has highly polished stainless steel finish. When you're selecting a prop for a boat, you must choose one that's appropriate for a boat and its intended use. Sometimes knowing which prop not to use is as important as knowing which props can be used. Careful choice of the right propeller will keep the engine running efficiently and keep your customers happy.